Hello and welcome again to another series of lectures in functional analysis. So today we will talk about weak topologies and weak convergence. Just to give you an idea or a motivation of this new topology, suppose I want to establish the existence of a weak solution of a certain partial differential equation, for instance. And this is, let's say we have a time-dependent PDE. To establish the existence of weak solutions, one strategy is what we call the Feydeau-Galerkin method. And for this method, the main idea is to consider approximate finite dimensional ordinary differential equations. And in this case, all these has been studied in detail. And here we can use, let's say, the standard, for instance, the Cauchy-Lipschitz theorem or the Picard-Lindelof theorem. To establish the existence of the solutions for your finite dimensional ordinary differential equation. What we would like to establish is that we want to prove convergence of these approximations to the suitable weak solution. So the key idea here is a convergence. And in this case, the topology induced by the norm more precisely, the metric induced by the norm may be strong enough that this convergence may fail. Okay, so in this way, we want some sort of a weaker topology. So there's a call for or a need for a weaker topology. That is a topology with fewer open sets. In comparison to the topology generated by the metric corresponding to the norm. So that's the main idea or our motivation in defining weak topologies. So to start, let us state the following theorem. And this was an exercise in the, or it was an item in the first exercise. So let us recall that in detail here. So consider a non-empty set X and a pair Y at T. sub y to be a topological space. And finally, consider an index family of functions from x to y. So for all lambda, let's say in some index set capital lambda. Let us define the collection S, script S, to be the set of all inverse images, okay, where V is open in Y and lambda is in the index set capital lambda. Then S is a subbase for the set X, and therefore the corresponding topology let's say denoted by T of S that is generated by the subbase is the weakest, or you can say smallest, topology on X such that the maps F lambda for all lambda are continuous. So this must be true for any lambda in the index set. So in other words, if you have, let's say, a topology wherein the maps F sub lambda are continuous for all lambda, then that topology must be larger or probably equal to this topology generated by the subbase S. So we will call this the topology generated by the maps F lambda. Okay, and an alternative notation. So we will also denote this topology as follows. So this is the topology generated by this family of functions. Moreover, we know that convergence of sequences in this topology is equivalent to the following. So xn tends to x, okay, in the topological space X equipped with this topology if and only if the corresponding images converge in the same way in the topological space Y for all lambda in the index set. So characterization of convergence in this new topology, or this topology on X, is equivalent to this convergence of the images in the target space Y. Okay, so now let's start with a Banach space. So we have the so-called strong topology on X. This will be denoted by T sub X raised to S. So S here for the word strong. So this is nothing but the topology generated by the metric, let's say dxy equal to the norm of the difference. And we know that this is a metric if this is the corresponding norm in X. Okay, so in other words, the strong topology on X is nothing but the topology generated by the distance associated with the norm of your Banach space. So if you have the strong topology, we also have the weak topology on X, and that will be denoted by a sigma. So we are following here the notation for instance in the book of Bressis or the book of Conway. So it is denoted by sigma x, x prime. Okay. So here x prime is the dual space of X. So this is the space of linear bounded functionals from X into R. So this is defined to be the topology generated by the dual maps or the bounded linear operators. That is the elements of the dual space. So here take note that X prime is a map from X into R. Okay, so this is of course linear and bounded. So in the previous theorem, okay, you can think of Y as the topological space. Okay, so this is your Y, and then you equip this with the usual topology. That is the topology generated by the distance corresponding to the absolute value. Okay, and from the previous theorem, we know that we know that this indeed is a topology. Okay, and moreover, so according to the previous theorem, this weak topology, okay, is the smallest topology such that the maps X prime into R are continuous. For all X prime in the dual space. Okay, since bounded linear functionals are continuous with respect to the norm, okay, or in other words, with respect to this metric, since X prime is continuous, or since each x prime in the dual space is continuous with respect to x having the strong topology and R with the usual topology. This implies that the weak topology is smaller or a subset of the strong topology. Okay. So take note that all bounded linear functionals in X prime are continuous with respect to the strong topology. And since the weak topology is the smallest topology for which these bounded linear functionals are continuous, then we have this inclusion immediately. So one might ask the following question. Are they equal? Okay. And if not, what are probably the necessary and sufficient conditions wherein this equality is valid? Okay. So, but before answering this question here, let us first describe a property of the weak topology. So if X, let's say, is a Banach space, then the weak topology is Hausdorff. So therefore, it is nice to know that our weak topology is Hausdorff, so that limits of sequences are unique. Of course, provided that they exist. So let us look at the proof of this theorem. So let us consider 2 points. Let's say X and Y in your Banach space that are distinct. What we do is we want to find 2 neighborhoods, open neighborhoods of these 2 points wherein these neighborhoods are disjoint. Okay. Now, by let's say a corollary to the Hahn-Banach theorem, applied to the difference, and in this case, the difference of X and Y is not 0. We can find an element X prime in the dual space such that the value of X prime applied to the difference. Okay, so here we are now using the duality pairing notation. Is not equal to 0. So there must be a non-trivial bounded linear functional wherein when we evaluate this to the difference, and obviously this difference is not equal to 0, the value of the bounded linear functional is not a 0 as well. And let us set epsilon to be, let's say, the half of the absolute value of this duality pairing. And we know, of course, that this is positive because this quantity here inside the absolute value is not equal to 0. Moreover, we set the following sets. So Ux this is the, okay, so let us take the inverse image of this ball. Okay, so this ball is the ball in R. So we are considering only bounded linear functionals that are real valued. And you take the duality pairing, but only with respect to X. So this is, to emphasize, this is the open ball centered at this point. So this is a real number with radius epsilon. So take note, this is a subset of R. And similarly, of course, by definition of X prime, this must be a subset of X. Similarly, we denote by, let's say, Vy, or let's say Uy. The corresponding set wherein we replace X, the argument X by Y. So according to the definition of the weak topology, these X primes are continuous. Therefore, the inverse image of these open balls are also open with respect to the weak topology. So Ux and Uy are elements of this weak topology on X. Now, we claim that before the claim, let us first note that, well, you can easily see this. X is in Ux and Y is in U sub Y. Because here, that would be the center. So when X prime is evaluated at X, you immediately get the center of the open ball. Or in this case, the open interval. So our claim is that these two neighborhoods are disjoint. So to show this, suppose on the contrary that the claim is not valid. In other words, suppose I have an element that is common to Ux and Uy. Then, if this is the case, let us compute, let's say, first this duality pairing. And we will add and subtract, okay, Z. And apply the triangle inequality so that you have the following. So here we use X minus Z, X prime, plus Z minus Y, X prime. So Z being an element of Ux implies that the first term is less than epsilon. And this Y, Z being an element of U sub Y implies that the second term is also less than epsilon. So this is less than 2 epsilon. Okay. And according to the definition of epsilon, okay, this is equal to the absolute value of this duality pairing, where the argument is the difference, which is not possible. Okay, so in other words, there cannot be or it is not possible to have a point that is common to ux and uy. Therefore, the claim is true. U sub y, u sub x and u sub y are open sets with respect to the weak topology that contains x and y respectively, and they are disjoint. And this proves the that the weak topology is Hausdorff. Okay, so we can separate two distinct points in X by open sets in the weak topology. So that's the proof of this theorem. So for the next one, we would like to generate a base. Okay, that is a collection of open sets with respect to a given point. So let us introduce some notations. So for a fixed point, x naught in capital X, a positive number R, and a finite collection of bounded linear functionals in the dual space. Okay, let us define the following collection: U x naught. Okay, and then paired with this finite sequence with the parameter R. And let us define this to be the set of all, let's say, x in capital X, wherein the image of, let's say, this difference, x minus x naught, with respect to this bounded linear functional is less than R for all j from 1 to k. Well, an alternative characterization of this is that, of course, you can write this as an intersection j from 1 to k of the inverse image of xj prime of the ball centered at R, or the open intervals with radius R centered at, let's say, x naught xj prime. By applying linearity, let's say. So you can easily recognize this equation. So having this notation, let us now prove the following theorem. Again, let us suppose that X is a Banach space. Then if I collect, let's say, a script U of X naught to be the collection of all these sets. Okay, so this is the collection of all U X naught xj prime R. So such that x naught is in X, R is positive, and xj prime is a finite collection of elements in the dual space. Of course, k is a positive integer. So this collection of open sets, okay, so it is, by the way, by the definition of the weak topology, all of this belongs to the weak topology. Therefore, the finite intersection of open sets in the weak topology is also open with respect to that topology. Okay, so this is an element of sigma of x prime. Going back to this theorem, this collection forms a neighborhood base at x naught, okay, with respect to your weak topology. So let us write here what do we mean precisely by this. So let's say given a point x naught in X and an open set U in the weak topology, we need to show that there exists an open set in this collection, let's say V, in this collection, such that X naught is in V, and this V is a subset of U. This is what we meant by a neighborhood base. So let us prove this. Again, starting with the definition of your weak topology. That is the topology generated by the subbase corresponding to the bounded linear functionals. It is possible to find, okay, there exists a finite sequence of bounded linear functionals, k a positive integer, and an open set, let's say O sub j in R, such that x naught is an element of, okay. Take note that the basic open sets in the topology generated by a subbase is a finite intersection of inverse images with respect to some open set. And this one must be a subset of V. It should not be V, but I should say U. That's the open set containing X naught. In particular, if I apply, let's say, X prime J to X naught, this is an element of O sub J. Since O sub J is open in R, and R is equipped with the usual metric topology, so therefore there must be, for each J, there must be an R sub J positive, such that the open interval centered at this duality pairing with radius R sub J, it must be contained in O sub J. Now, by taking, let's say, R to be the smallest of the radius among the radius, we have the following. So x naught would be, okay, you take this open set in the weak topology. So x naught, you take this finite sequence of bounded linear functionals, and then you take this R. And this one is a subset of this set here. And by transitivity, it must be a subset of U. Okay, so you can take this as your V. In this line here. And that's the end of the proof for this theorem. So you have some sort of a neighborhood base corresponding to this point x naught for the weak topology. So let's now go back to this question that was posed a while ago. Are these two topologies the same? And if not, what are the instances wherein these are equal? And this will be our goal in the following theorem. Again, X is a Banach space. Then the equality of the weak and strong topologies on X holds if and only if X is finite dimensional. So for a finite dimensional space, Banach space, the weak and strong topologies coincide. However, for infinite dimensional Banach spaces, this is not true. So you have a strict inclusion between the weak topology and the strong topology. And let us prove this. So let's start with the case where your Banach space is finite dimensional. And let's say x1 up to xn be a basis. For this finite dimensional Banach space X. Okay. Now each vector in X has the unique representation in terms of the basis elements. So X can be written as a linear combination of your basis elements, where alpha j, let's say, are scalars. And let us focus on the real case. Now we consider the coordinate functions. Xj prime. So this is a map from X into R as follows. So the value at x is just the jth coefficient. In other words, the coefficient of the jth basis vector. Then, okay, you can easily show that this is bounded and moreover it is linear. Hence, these coordinate functions, of course, j from 1 to n, is an element of the dual space of x. Now let us take a fix x in capital X and a positive r. If y is in the ball centered at x with radius r, okay, looking at the what's this? Looking at the distance between y and x. Okay. Take note that this is the same as the norm of the following linear combination. So the coefficients here are the duality pairing. Then you have here your basis vectors. And why is this? Okay, of course, alpha sub j's here is basically your value of the bounded linear functional at that vector x. So replacing x by the difference, you have these coefficients. And if we apply the triangle inequality and the homogeneity of the norm, you have this. So the norm here is, of course, taken in x. If we denote by, let's say, m, the largest among the norms of your basis vectors, then you can easily see that this is less than or equal to, or yeah, this is less than or equal to m times the sum of the duality pairings. Okay, and from this, you can immediately see that the neighborhood u of y corresponding to this bounded linear functionals and let us take, let's say, the radius r over mn is a subset of the ball centered at r with radius x. And why is that? Okay, so let us explain here. If you pick a point, let's say, and there's a correction, there should be an x. So if you pick a point, let's say a y in this space. So if you pick a point y on this space, we want to show that it is also in this ball. So this does not make sense. So let's say let y be an x. Okay. So starting from here, let's say you have a point y, then each of these must be less than r over mn. Okay, and you take the sum n times. So that's the n in the denominator will be cancelled. You have here a factor r. I should say a factor m that will be cancelled, and this is less than r. So therefore, y must be also in this open ball. So the above estimate implies that this is the case. So let us we should have a y here, of course. So this must be x, I should say. Yes, this will be, of course, the case. So let's start with, let's say, let u, or let's say v, be an element of your strong topology. Then, and for each x in v, we can find, let's say, an r. So there exists an rx, okay, in a positive, okay, rx, such that the ball centered at x with radius rx is contained in v. This is basically the definition of your metric topology. From above, okay, the above discussion, we know that there exists, let's say, a constant as x, okay. So let us say that this is s of x, positive, and okay, such that ux xg prime j from 1 to n uh, sx is a subset of brx of x. Thus, okay, if we take the union over all x in V of these elements of your neighborhood base, okay, surely this is a subset of BRX, x in V. Okay, and this is what? This is equal to V. Since all of the balls are contained in V and it contains the radius. And you can also say that this is equal to V. So to summarize that one, therefore, you have this equation. So now we know that this is open, with respect to the weak topology. So union of open sets is again open. So this implies that your V is open with respect to the weak topology. Hence, we have the strong topology is contained in the weak topology. Since the other inclusion is always true, we now conclude the equality of the strong and weak topology. So this inclusion here is due to this fact. Okay. So that's the case of finite dimensions. The weak and strong topologies are the same. Now let us prove this direction. And we prove this by a contraposition. In other words, if X is infinite dimensional, then we show that the weak and strong topologies on X are different. So in other words, the weak topology has strictly fewer open sets than the strong topology. So the idea here is to consider, okay, to consider a finite collection of elements in your dual space. And a positive R. Our claim is that there is a non-zero, say X, in your vector space or in your Banach space. Okay, so to denote that, let us use Y, okay, such that the span of Y. So think of this as what? As a line spanned by your vector Y. Okay, this is a subset of the following open set in the weak topology. So let us establish the claim first. Based on this finite collection of bounded linear functionals, we define an operator from X to Rn as follows. So this is, let's say T of X is the following vector. You take the duality pairing. And here we do not write the supers or the subscripts for simplicity. If the kernel of T is 0, okay, then T as a mapping from X into its image would be bijective. Okay. So if the kernel is trivial, then it is one-to-one. Okay. To make the map onto, you restrict the codomain onto the range. since T of X is a subset of Rn, T of X is finite dimensional. So if you have a linear, so this you can easily see that this is linear. A linear map, which is an isomorphism, okay, preserves the dimension. Of course, provided that your vector spaces are finite, both finite dimensional. So in this case, X is also finite dimensional, which is not possible because we know here we assume that X is infinite dimensional. So based on this, let us consider an element of the kernel of n that is not 0. And based on this, take note that for each, let's say, j from 1 to k, if I take the duality pairing of y, and this is our center, okay, or our reference point 0, xj prime, this must be a 0, since t of y is equal to 0. So if t of y is 0, then replacing x here by y, all of these components must be 0. Therefore, you have this. And if you take the absolute value, of course, this is less than r since r is positive. Hence, if you apply linearity as well, okay, if you have an alpha, you can, of course, factor out alpha and still have this equation. So probably we could write it here. T of alpha y is alpha t y, and this is 0. This inequality shows this inclusion here. So any element of the linear span satisfies this inequality for each j. So therefore, the span of y is in this neighborhood. So the open ball, okay, in the strong topology. So this is the set of all x in your Banach space wherein the norm is less than 1. We know that, of course, in the metric topology, this is open. So this, in other words, this is open with respect to the strong topology. Let's say this is the center. And you have a radius 1. So think of, let's say, the interior of this circle. Of course, the clutch here is that this is not an appropriate representation because we have an infinite dimensional Banach space. But let's see what is the corresponding result. Okay. So we have a vector y, okay, in the let's say in the kernel, okay, of T. So let's say let us take alpha y. So y is not 0, okay, and I should correct this to 0. Since that is the center, okay. We want a y or alpha y that lies entirely, let's say, on the open ball, okay. So it is possible that y is outside. It is possible that y is inside, okay. Let's say y is outside the ball. Well, it doesn't matter, since if we take the line determined by this point, you will get something like this. And let's move y here. So it can be here, it can be here. Nevertheless, you have this line. So this line is contained in let's say u, zero, xj prime, j from 1 to k, r. So this implies that, okay, the open ball b1 0 is not an element of the weak topology, since, okay, if this is not the case, so let's say suppose it is open, okay, then 0 being an element of b1 0, according to our previous theorem, we know that there must be an element of the neighborhood base. So in other words, there must be a finite collection in the dual space and an R such that this neighborhood base or this particular neighborhood is a subset of your open ball, which is not possible since we know that there is a y non-zero such that the span of y is a subset of your of this neighborhood in the weak topology, and of course it is obvious that span of y, since y is not 0, is not a subset of your open ball. So here you have let's say you have this inclusion. We're saying that this is not possible because this line must be contained in the set U. Okay, we cannot draw here the set U, but imagine that this line here is contained in U. But obviously, this line is not in the open ball. And why is that? You can just scale this in such a way that alpha I would have a sufficient large, let's say, norm. So for instance, what if we, let's say, divide this by the norm? Okay, this one is an element, obviously, of the span of y. So we normalize it. Okay. However, this is obviously not an element of the open ball, because here the magnitude is precisely 1. Okay, so the open ball in X is open with respect to the strong topology, but it is not open with respect to the weak topology. So we now conclude that the weak topology on X is a strict subset of the strong topology on X. In particular, they are not equal. So let's now study convergence with respect to the weak topology. So take a sequence, let's say xn in X and an element in your Banach space X. So we say that your sequence converges weakly to X if the convergence hold with respect to the weak topology. So that is if xn tends to X in X equipped with the weak topology. And for this, we will adapt the following notation, where you have an arrow only on the top. Okay. And I think in LaTeX, this is you can use the command left harpoon up, or I should say right harpoon up. And we should have a subscript here. So this will be a shorthand or a notation for this phrase that the sequence converges weakly to X. So before we discuss in detail the weak convergence, let us start with the following lemma concerning about the bidual of Banach space. So the map Jx from X into X double prime, and by definition, this is the dual of the dual space. And is given by the following. So Jx of X, so X here is in capital X. So if Jx is in the bidual, it takes an element of the dual as the argument, as an argument. So here you now have the duality pairing between x prime and x double prime. And this is defined as follows. So what we do is we just take the duality pairing of x and x prime with respect to the corresponding function spaces x and its dual. This one is a linear. It's a linear isometry. And we shall call Jx the canonical embedding of x into the bidual. So since this is injective, you can think of elements in the bidual space as having more elements than the space x. And by identifying x and the image under this canonical embedding, we can treat x as a subset of x double prime. This is the bidual of x. And let us look at the proof. So the proof utilizes again the Hahn-Banach theorem. If I have an element x in the Banach space, take note that, okay, of course, this is j, x of x evaluated at x prime. Okay. So let us compute this. Take the magnitude. This is less or equal to, according to this definition here, and applying the property of the dual norm. So this is less or equal to the product of the dual norms. You can easily see that this mapping is linear. Okay. Since here the duality pairing is linear with respect to both arguments. Here we are considering a real Banach spaces, of course. This estimate implies that Jx of x is is linear and bounded. So therefore, it is in the bidual space of x. And we have the following. Okay, so by the definition of the dual norm, or in this case, the bidual norm, this is okay. If you take this to be less or equal to 1, or let's say equal to 1, then you have this inequality. Well, I will leave the details to you, but it is easy to verify that this map is indeed linear. And here, because again, as I said, the duality pairing is linear in both arguments. Now, suppose I have a non-zero x. From a corollary of the Hahn-Banach theorem, there exists a bounded linear functional, say x prime, x prime not, okay, such that it has a unit dual norm and the duality pairing is equal to the norm of x. From this, it follows that, okay, Jx the dual norm, okay, is greater or equal to the bidual norm, okay. So let's write here the definition first for clarity. So this is the soup over all x prime in the dual space having norm 1 of uh, this quantity. I should write x prime here. J, or let us write this way. X prime, okay. And if I pick a particular x prime, namely x prime not, so we have this inequality. But then, according to the definition of your J, this is equal to the duality pairing okay. But since the norm is non-negative, therefore the absolute value of this is itself, and we know that this is the norm of x. So we now have the reverse inequality. Okay. For all x in capital X. Now, here the argument states that x must not be 0. But here it is obvious that this equation holds when x is 0 because both sides will be 0. Okay, so we can append when x is 0. Okay, so that's the reverse inequality. And this proves that Jx is indeed a linear isometry. Okay. As promised, let us now discuss in detail the weak convergence. As usual, X is a Banach space. You have a sequence in X, and let's say another sequence in the dual space. So the first conclusion is that we have weak convergence if and only if the duality pairings applied to a particular element of the dual space tends to this one. For all x prime in the dual space. Okay. What is the proof? Follows from the definition of the weak topology. And why is that? Of course, these duality pairings are nothing but the value of x prime at xn. Okay. And going back to our previous discussion, we applied this comment here. Let's say this is star. Okay. So we apply this, and you have this conclusion as an immediate consequence. Okay, so the first one is nothing but the definition of weak convergence. Okay, written in an equivalent way. Next, if we have strong convergence, that is convergence with respect to the norm, then we also have weak convergence. In general, I would like to mention here that the converse is not necessarily valid. So let us look at the proof. Okay, for a weak convergence, we would like to apply 1. Okay, so it is enough to verify this convergence here. So this follows from 1 and the fact that, okay, so let us estimate the difference of the duality pairings. Here, I will not emphasize the subscripts, okay. According to the linearity of x prime, this is equal to this duality pairing. And applying the property, okay, so this duality pairing can be bounded by the norm of the difference and the dual norm of x prime. Here, of course, x prime is in the dual space. This guy here, it tends to 0 as n tends to infinity, since we have strong convergence. Okay. Since x prime is a fixed, okay, element, this tends to 0 as n tends to infinity. So the limit of the difference, or the magnitude of the difference, goes to 0. Therefore, this one goes to this one. And applying 1, we have a weak convergence. Again, strong convergence implies weak convergence. Next, if we have a weak convergence, then your sequence is bounded with respect to the norm. And here we have the norm of the limit is less than or equal to the limit inferior of the norms of the terms of the sequence. So put in another way, a weakly convergent sequence is bounded. And the second statement means that the norm functional is weakly lower semi-continuous. So by this, we mean that if we have a sequence that converges weakly to x, the norm of the limit is less than or equal to the limit inferior of the norms. Okay, so that's the first statement. The second one is namely this one. Okay. And this is the place where we use our previous lemma. Okay, so suppose I have a weakly convergent sequence. Then 1 implies that, okay, this is convergent in R, okay. For all x prime in the dual space. Now, if we utilize, let's say, the Banach-Steinhaus theorem to the following sequence of functions, we take the canonical embedding, okay. So this is a subset of x double prime, and we know that this is the set of bounded linear operators from x prime to R. Okay, so applying the Banach-Steinhaus theorem to this sequence, we know that, okay, this we have this uniform boundedness. Okay, since Jx is an isometry, so here we now apply the previous lemma. So the norm of Jx xn is equal to the norm of xn in x. Then let us apply the soup. And this proves the boundedness of your sequence, of your weakly convergent sequence. Now, to prove the weak lower semi-continuity of the norm, okay, namely this inequality here, okay, it is enough to assume that the limit is not equal to 0. Because here, if x is 0, then whatever the limit here, the limit inferior, well, this exists because our sequence is bounded from below, okay, in particular by 0. This inequality is trivial when the weak limit is 0. So it is sufficient to assume that x is non-zero. Why? We want to apply the Banach theorem, or more precisely, a corollary to it. There exists, let's say, an x prime in the dual space such that this is a unit vector in the dual space, and this duality pairing is the same as the norm of x. Then, okay, starting at the norm of x, Okay. Since this is non-negative, we can apply or put the absolute value here. According to 1, this is the same as, okay, the limit as n goes to infinity of the sequence of duality pairings. Of course, the limit exists, so therefore the limit inferior is also the same. And take note that this duality pairing, the magnitude of it, can be estimated by the norm of xn times the norm of x naught prime. This one is 1. Yeah, this is equal to 1. Okay. If you now take the limit inferior, you have this weak lower semi-continuity of the norm. So again, this third part of the theorem states that a weakly convergent sequence is necessarily bounded, and your norm, considered as a functional from x into r, is weakly lower semi-continuous. And finally, we have the following. If I have, let's say, weak convergence in X and strong convergence in the dual space, so here with respect to the dual norm, of course, then the sequence, the following sequence of duality pairings tends to the duality pairing of the limits. The proof here so what we do here is that we show that this absolute value of the difference must be as 0 as n goes to infinity. The limit is 0 as n goes to infinity. So let's add and subtract a term. Okay, this is, let's say, minus x. Okay, and we need to add this. So we have xn x prime minus x prime. And now let us apply the triangle inequality. So this is less or equal. We can bound the first term by the norm of xn and the dual norm of the difference, while the second term is the same. We now focus on the first term, the second term. So this one tends to 0 as n tends to infinity, since xn converges weakly to x. By the first property. This one tends to 0 according to the definition of a strong convergence with respect to the norm. Okay, the assumption here, and this is bounded. Okay, so you can have a fixed upper bound. So if this is bounded, this product here will tend to 0. So to conclude, this tends to 0 as n tends to infinity. And this is precisely this convergence here as n tends to infinity. So once again, if you have a weak convergence in X and you have strong convergence in the dual space, then taking the duality pairing of the associated terms, okay, the set of duality pairings will converge to the duality pairing of the corresponding limits. So in the next lecture, we will consider weak topologies on the dual space.